So again, I'm very happy to be here. Thank you for inviting me. And I'm going to tell you about graph partitioning in Truett. And my interest in the subject started with the following conjecture of Chartrand, Gellin, and Herednimi, that every planar graph is a union of two outer planar graphs. And when I heard this conjecture, I thought for 15 minutes, and I thought to myself, I know how to do this, I think. And this is what I thought. Okay, without loss of generality, G is a triangulation. And then if, that's an if in addition, G is 4 connected, then Whitney's theorem says, well, it's Hamiltonian. As long as you have a Hamiltonian cycle in the planar graph, that cycle and edges inside of it, that's an outer planar graph. And the cycle again, and the edges outside of it, that's another outer planar graph. So there you go. I mean, that's your decomposition. That's your partition of a planar graph into two outer planar graphs. Well, except that there was an if. There was an if, that if G is 4 connected. So what if it is not? Well, then the minimal counterexample, of course, if it's not 4 connected, then there is a 0, 1, 2, or 3 sum of smaller graphs. So what I have to do is decompose each of those and make the parts fit together. And notice this was kind of promising because you have a lot of extra information here. That is, first of all, there's not just one Hamilton cycle C. I mean, Whitney's theorem says it's Hamiltonian, but Fast's theorem actually lets you move that cycle to your, well, to some position. You can say some of the specified edges are in the cycle, so that forces some of the edges inside of it and some of the outside of it. Another benefit that you have going for you is that, in fact, you're interested in partitioning the graph. So some of the edges of the cycle you can declare to go with the edges inside and some others with the edges outside. So that was helpful. That was helpful. Fail. It didn't work. We couldn't do it. No, that didn't work. We couldn't do it. It turned out that later, maybe if we had worked harder, we could have done it, but somebody else did it. Later, it was proved true by consultants. But the reason that we didn't work as hard on it perhaps as we should have was because we got distracted. We got distracted because we had in fact proved that every planar graph is a union of two series parallel graphs. And since this is a conference on tree width, I can rephrase it. I can say that every planar graph is an edge partition into two graphs of tree width at those two. And that's where we got distracted. We said, all right, how about other surfaces? Can we do the same statement, not for planar graph, but for projective graphs, graphs that go on the projective plane? And the answer is yes. Yes, every projective graph is a vertex partition into two graphs of tree width at those two. All right, great. So what about the torus? Can we do it for the torus and the Klein model? And the answer is kind of. Well, for the torus and Klein model, which have Euler characteristic 0, we have a vertex partition and an edge partition, in fact, into two graphs of tree width at most 3. So we have to give up one. And in fact, giving it up, at least for the torus, was necessary. We can easily prove that, in fact, there are toroidal graphs that cannot be edge partitioned into two series parallel graphs. All right, so we did it for the basic surfaces. So how about all surfaces? And the answer is yes, we can do it. Of course, we have to give up the tree width at every stage, but not by much. So every graph G has a vertex partition, which means you can partition its vertices into two classes, so that the induced subgraphs have each tree width at most 6 minus 2, the Euler characteristic of G. So of course, Euler characteristic of G is negative for most of the surfaces, so in fact this number grows as the complexity of the surface grows. And for edge partitions, this is not too bad. For edge partitions, this is 9 minus 3 times the Euler characteristic. All right, so we've done it for every surface to an extent. Notice, by the way, that this here, when you apply it with the Euler characteristic 0, of course you get a worse result in this general formula that we did for specific versions of the torus and the Klein model. But I'm going to tell you now how the proofs go. The proofs are, in a sense, quite simple in principle. The proofs say this: set a vertex and a vertex, and let Vk denote the set of vertices, distance k from it, and then even and odd. That is, divide the vertices, divide the sets Vk and group them together when k is even, and group them together when k is odd, and those are your two sets for the vertex partition. And for edge partitions, you are going to take the edges that go between vertices in Vk and Vk, and between Vk and Vk plus 1, and again, do even and odd, and it works out. Now, I'm hiding a lot of ugly mess. I mean, you have to prove that, in fact, everything works out, and it does, but it's a little more complicated, let's say, than this suggests. Okay, but, so we've done it for surfaces. Can we extend it even further? Yes, as well, of course, we can do it for surfaces. Chances are you can do it for graphs which are coming from minor closed classes of graphs. And in fact, Robin Thomas posed the following conjecture. He said, for every g, there's an integer k, such that every graph without g, this one graph is a minor, has a vertex partition and an edge partition into two graphs whose g width is less than or equal to k. And that k depends only on that graph g that you're excluding. And by the way, if somebody doesn't remember what minors are, here's a little reminder. I'm not going to read it. And in fact, we could do it. So notice this is now a longer list of authors. This is Ding, myself, Sanders, Vertigan, Matt DeVos, Bruce Reed, and Paul Seymour. In fact, we didn't all collaborate together. We just found out that there were two papers going on in parallel before they were submitted, and so we merged them because they were basically identical. And so now we have a larger list of authors on basically the same result. And it's exactly, well, it looks a little more general than what Robin said, but it really isn't. That for every minor closed class of graphs, other than the class of all graphs, you have this number k, such that every member of the class you can partition, a vertex partition and edge partition, your choice, into two graphs whose g width is bounded by this k. Minor closed class of graphs, well, again, I'll leave it to you if you don't remember what it was. And of course, there's a theorem of Robertson and Seymour says that all members of a minor closed class of graphs, other than the class of all graphs, are clique sums of graphs that are almost embedded on surfaces of bounded genus. And so, of course, we could use our idea, except that the proof doesn't go directly as I suggested before. You cannot just use the distances, because those almost parts, I'm not going to go deeper into what they mean, but they, in a sense, do not follow the surface. So we have to somehow make those almost work out in another way. Fortunately, that almost, of course, has some bounded complexity, and you have something to work with. So I'm not going to go into the details of that proof. And finally, on the screen is that, well, every minor closed class of graphs can be characterized by excluding finitely many graphs as minors, so the transition from just excluding one graph to minor closed classes is obvious. Okay, so we have done basically as much as we could, because you really cannot think about the class of all graphs and hope that you're going to get something useful, because all graphs have cliques, and cliques have just too many edges to allow any useful partitions. For example, if you wanted to look into edge partitions into graphs, there is simply the number of edges grows too quickly in complete graphs. So James Oxley asked the following question: can you do it for co-graphic matroids? There, the counting principle doesn't quite get in your way. That is, he asked very specifically, can every co-graphic matroid be partitioned into two series parallel matroids? Now, I'm not going to tell you what matroids are, although you know, probably. What I'm going to do is I'm going to translate it into a question about graphs, because this is a question about graphs. This is the translation. That is, can the edges of every graph be partitioned into E1 and E2 such that each of G contract E1 and G2 contract E2 is series parallel? Notice every. I don't care about surfaces anymore. Well, I will in a little bit. But the question does not. The question says every. Well, so a student of, the answers. The answer is yes if it's planar. I mean, we proved it for planar graphs, so you can just dualize the whole theorem that we proved, and you get this. Because partitions, as we spoke before, were exactly these kind of things, except we had delete here instead of contract. So we can just dualize the whole proof that we had for partitioning planar graphs into series parallel graphs, and you have answer to questions of Oxley. More surprisingly, perhaps, the answer is yes, if the graph is four-connected. Because every four-connected graph, according to Nash-Williams, has two edge-disjoint spanning trees. If you have two edge-disjoint spanning trees, the game is over. You just color all the edges in one spanning tree red, all edges in the other spanning tree blue, the other edges, whatever you like, and when you contract either color class, you have nothing, just a vertex with loops. So I had another bright idea that didn't work out. The bright idea was, well, all right, so the only thing that is missing is, graphs which have 0, 1, 2, and 3 separations. So minimal common example cannot have a 0 separation, cannot have a 1 separation. All we have to work out 2 and 3 separations, and we couldn't. So Evan Morgan, who was a student of mine fairly recently, we proved that for the projective graphs, we can do this if we give up the tree width by 1. And for toroidal graph, we can also do it if we give up, well, one of them we can keep at tree width as 3, the other one we can keep at tree width at most 4. From there, things got messy. So we didn't do it for the Klein bundle because, well, it got beyond our hand. Now there is a theorem which is general. The theorem that's general is this. The edges of a graph of genus G can be partitioned into two sets, E1 and E2, such that each G contract E1, G contract E2 has tree width which is big O of G squared. That's the theorem of the main Hagi and Mohar. So notice that the tree width in their case, because here has G squared in it, which is the genus. That is, you count number of handles and number of crosscuts, multiply number of handles by 2. Now notice that in a sense it subsumes our result, and in effect it does, but the numbers that you can extract from their proof are significantly worse than what we could prove directly. So what we did, and this is new, those two results haven't been unpublished yet. Those two results are significant improvement on this. All right, so let me ask you about time.
Okay, you have about 10 minutes.
10 minutes, okay, great. So this is as much as I can say about partitioning graphs of through contraction. So now let's talk about partitioning graphs which we know we can partition into graphs of bounded tree width, namely graphs of bounded tree width themselves. And let's see what we can do. And so let's start. I'm going to tell you about some special kind of a K-tree. So let's go through this definition. So what I'm going to talk about is T with indices K, L, and R. And this is how we are going to construct such a thing. So here's a picture as we go along. I'm going to show you. We are going to start with K sub K. So this 2 indicates how big a clique we start with. And this is, we declare those two vertices and this edge between them. We are starting with K2 as being at level 0. And then inductively, for every K sub K subgraph H of level n minus 1, we are adding R. R is the repetition number, so to speak, of new vertices. We join each of them to all vertices of H and declare all newly created vertices and K sub K subgraphs to have level n. Right, so we have level 0, we are working on level 1. So there's only one K2, so we add one vertex because our specified value for R is 1, and we connect it to all the vertices, and then we declare these things to be level 1. And then we repeat. That is, we have now 2 of those K2s. So for each of them we add a new vertex, and we join them to the ones below, and we continue, and well, we stop until we have created the level L subgraph. I wanted level 4, so this is it. This is an example. This is the picture of T241. So a definition of a K-tree, I mean all of you know what K-trees are, but here is another way of looking at it, that you can view it as this graph that I just described, where L is arbitrary. You can go with L as much as you want. And at every stage, you don't have to do R copies of the new vertex. You can just vary it to whatever you want. And that's a definition of a K-tree. And here is a theorem, again, Ding, Oxley, Sanders, and Oregon, is that we have, if we have K1 plus K2 plus 1 tree, we have a vertex partition into a K1 tree and K2 tree. That's not surprising, this is easy to prove. This one also is not surprising, it's also relatively easy to prove, a little harder but not by much, that if we have a K1 plus K2 tree, then we have an edge partition into a K1 tree and a K2 tree. Okay, so now let's see if those results are in a sense the best that we can do. I mean, let's look at this. If we have K1, K2, L, and R given, then we say there is a big L such that if you have a vertex partition of the K1 plus K2 T with K1 plus K2, L, this big L, R is kept the same that it was, then either side, one of the sides, one or the other, contains TK1LR or TK2LR. So we could prove that if you partition this into two parts, then one of the parts must necessarily contain this, or the other must contain that. So what about a corollary of this that says if you have, again, K, L, and R, you can find a big L. That is, you can just have to increase the number of levels, but you can keep all the other parameters of that tree T, K1, K2, LR, such that at least one of the GIs contains T1, LR. So if you partition this into K, K being the same as that, then at least one GI is going to contain this big generic one tree. Okay, this is for vertex partitions. So can we prove it for edge partitions? And the answer is no. We cannot prove it. We can conjecture it, which is much easier than proving. Here's a conjecture that basically is an exact copy of this conjecture, almost. Well, of course, there's an obvious difference between edge partition and vertex partition, but there's another change, which is subdivision. And I say, we have to put the word subdivision because without it, it doesn't work. Let me show you why I need the word subdivision here. It doesn't work if this word is removed. So let's go back to our friend T241, and I'm going to give you an edge coloring. Okay, I'm going to give you an edge coloring, and I'm going to try to convince you that neither color class of those edges contains a big T141. So I'm going to start by coloring the vertices. That's just an auxiliary part of the process. So each vertex I'm going to color red, green, or blue, and in fact I can do it uniquely. There's not much choice here except for permutation of colors. So here's the coloring, and now I'm going to color the edges. And this is the rule for coloring the edges. If I have a green vertex, so I was going to color the edges either going right or up. So if I'm going right, well, it is only one time that I go right, but nevertheless, if I go right or up from a green vertex, it receives color which is other than the other endpoint. So here it is. So green went to blue, it received red. Green went to red, the edge received blue. Now, for the remaining edges, I'm going to color them based on the initial vertex. That is, this red is going to be all reds, this blue is going to be all blues, like this. And this, by the way, generalizes to other trees of this kind. So this is not specific to the case when this is 2, 4, and 1. You could do it for any tree of that kind. And I'm going to try to convince you now that you don't have a big blue tree of the form T141. And why not? Well, let's look at the blue tree. Let's see what happens at the blue path. Well, if I had a big blue tree like this as a subgraph, I would have to have a path of length 4, all blue, such that the blue degree would have to be more than 2, 3 specifically, at least 3. Because if you take a big binary tree as a subgraph, you have a long path of vertices, consecutive vertices, which are of degree 3. Well, where are they hiding? Well, it cannot be, we cannot use really a green vertex, can we? Because look at what happens to a green vertex. If we enter a green vertex, what happens is we go up we go, in a sense, to the wrong edge. We go here, we end up at a red vertex, and we cannot go up anymore. Well, I'm not going to go through the details, but this is easy to convince yourself. It's easy to convince yourself that indeed you don't have a good tree like that. So, what about that conjecture that we made? Maybe it's completely wrong, and here I support the evidence, I give supporting evidence that maybe it's right after all. Remember, this kind of a statement was true without the specific values of 2 here. It was just K before for vertex partitions. But for edge partitions, this is the best we can do. That in fact, if we have 2 L and R, then there are 2 numbers. We have to give up on R before. Remember, before R didn't have to be changed, but now it does. Then it contains either a red T1LR or a blue subdivision of this. Okay, how am I doing the time?
Just a minute or two.
Just a minute or two. Okay, so last thing I would like to tell you is about partitioning of graphs so that you only get small components. And the obvious thing to look at is you have to bound a maximum degree and you have to bound the tree width. And here are some statements that says if you have a maximum degree bounded and you have tree width bounded by K and maximum degree by delta, then there is a vertex partition into 2 graphs of components of this many vertices. And there is an edge partition of G into 2 graphs with components on only this size. And I would like to convince you that just bounding one or the other is not enough. So obviously, is it bound enough to bound just the tree width? And the answer is for edges, definitely not. Take a large star. If you take color classes, if you color the edges of the big star, you're going to get a big color class. And of course, that's all connected. But maybe you could do it for vertices, and the answer is no. A large fan will prevent you from doing that. Can you bound just the vertex degree? And the answer is no. 4 regular graphs can have arbitrarily large tree width. That's according to Erdős and Sachs. And if you have a 4 regular graph of arbitrarily large girth, let's see what that means. Well, that means if you try to subdivide it into 2 parts only, one part would have to have a cycle. There's too many edges in a 4 regular graph for both parts to be acyclic. So you have a cycle, but large girth means no small components. And so one part of an edge partition would contain the cycle. So bounding maximum degree just as 4 is not good enough. Well, what about vertex partitions? Take the line graph, and you have nothing to work with because line graphs of 4 regular graphs are 6 regular, so it's not enough to bound at 6 or more. So what about smaller values, 3, 4, and 5? Well, for 3, 4 vertex partitions, there is a theorem of Thomason that they do admit such partitions. What about 4 and 5? Let me tell you that we proved that we could do it with 57 vertices. And we immediately beaten to the punch by Haxel, Szabo, and Tardos. They said 57 can be reduced to 6. And by the way, this is close to being best possible. 5 is the best power. Now 5 is a lower bound. What about 5? That is, what if you bound the maximum degree by 5? Then they also provided the answer. We posed it as a question, although they are probably far from the best possible number. Okay, I'm going to stop this. Thank you.